Alright, let's do a little demo of my renderer, which I developed during my thesis. The topic of the thesis was clustered light shading, an optimization technique for rendering with many light sources, culling them more effectively than per camera. But what you do is essentially divide up the camera or the visible space into many smaller clusters, like what you can see here. Then for each of these clusters you compute which lights are relevant and only use those lights while shading your scene. What I did is extend this technique to work in for stereoscopic rendering, making use of the coherency between both eyes and only doing the clustering once instead of twice. As you can see here, the red frustum is the one I used to create the clustering, then the two green frusta for the eyes. And yeah, this is what it does. I have a couple of ways to visualize the number of lights per cluster. This is like more of a heat map, white being around 25 lights, so you can see kind of how many lights fall off into each cluster. If I, on the left here, change the intensity of the lights, their radii become larger and therefore more lights fall into the clusters. I can increase the accuracy by which the lights are represented further, increasing the light radii. I can show the light radii. Where would that be? Render the volumes true. So there's quite a bunch of them actually in this scene. Decrease the falling light count a bit, maybe the intensity and the fall off. So that's the project. Pretty cool. This application was developed in Rust, which is a relatively young programming language, and the code base isn't perfect. Of course, there's many things that could be improved, but overall I think it's quite neat. I have profiling information that can be collected and stored offline or displayed immediately, as I'm doing here. And we can see, let me get back to 1,000 lights and then don't render those. Alright, so if we look at the timings here, I'm going to pause the simulation of the lights. You can see how long different parts of the rendering pipeline take on both the CPU and the GPU, where there's a depth prepass, for example, which takes around 500 milliseconds for the bistro scene. Then there's the clustering pass, which takes about a millisecond. And then there's the basic shading pass, which takes most of the time, around 3 milliseconds for this, under these circumstances for this view. The meshes of the scene are cold per camera, so if I don't see the mesh, I'm not drawing it, which has a big influence on the performance, of course. There is support for transparent geometry, although I'm not doing any sorting, so that means that if you look at it from the wrong direction, things will look kind of odd, as here one glass bottle is drawn on top of the other one when it really should be behind. I implemented order-independent transparency at some point, but because it makes the code harder to maintain, I kind of left it out so that I'm more flexible, making changes that were actually required for my thesis. Do I have anything else I'd like to show? Let me go through this. I think that's pretty much it. What I really wanted to do is extend this work to allow shading or allow the clustering to work for multi-view scenarios. So this is using the traditional clustering method, which creates these blocks. What I've done is also use a more regular grid like so, where each block is kind of defined in camera space rather than post-projective clip space. And what this allows you to do is have multiple cameras overlapping with any orientation, and then reuse the clustering from them to do that. This can be useful when rendering reflections, for example. But I haven't gotten to that part yet. Thank you for watching. That was a little demo of my project. I hope to see you at some point. Bye-bye.